but we haven't yet gone into CNN. So today we will recap what we discussed previously so that we can build on top of that. So remember, we started discussing about computer vision, where we said different kind of problem, image classification, image segmentation, different kind of problem that in computer vision, you can do different kind of tasks. For example, binary classification, multi-class, and whatsoever. We also discussed saying we're gonna follow this pipeline, if you remember, how we can get our data set, using some of these transform data loader, and we're gonna use basically some models from Touch Vision because we are using image stuff, which all the models are here, and we're gonna use metrics from Touch Metrics. Here we remember we load everything, including the Touch Vision and data set, which are on Touch Vision. We also load to Tensor, which allow you to convert image from any kind of representation to Tensor. And okay, we said, okay, we're gonna get started, but what are we going to do? We said, all right, what we are going to do is to train a simple classification using fashion MNIST dataset. So this is a dataset. The dataset, what it contains basically image of, fashion stuff like trousers, shade, and whatsoever. And we know because we have multiple classes, this is called multi-class classification, right? Because it has different classes. Now we say, okay, so in PyTorch, how are we going to get the data set that we are going to use? Then we said, all right, PyTorch brings a lot of stuff that allows you to do that, which the data set is here, is off-the-shelf data set. And we can call the data set from data set, bring fashion MNIST data set. So when you want to download any data set from PyTorch, you just say data set and then fashion MNIST data set. Remember here, this data set, we already loaded here. You can see from Touch Vision import data set, right? So here we have said, okay, but this is training data. So this argument, this function allows you to specify what is training data whatsoever. So here we said root data, where it will save the data. Train, yes, train, download, yes, download it, and transform the data into Tensor. Transform, because we're gonna use everything in Tensor. And now transform, get transformation now. So you can see here also for the test data, and we have this. So we can see here now we have, everything. Food. All right, we can see now here we already have our data set. And now the next thing is let's look at the data. I'm just recapping this one. We already did this, so I'll go faster. If you missed the previous session, you can go back with detailed explanation. We can see this is the training data. How many data points? We have 60,000, right? And this is some of the information about the data, and we can see train data, the 0, the first one. When we have this, then we say, let's see, because when you call the train data, it will return a tuple. The first thing that it returns is the tensor for the object, and the second one is a level. So the train data that we grabbed here, it returned two things. The first one, if you look at it here, you can say here, yeah, you can see here, which kind of split it is a train, and the location where it is saved, and this is the 60 data point. But the data, we know if you want to do machine learning, it must have future and what? The target, right? So when you call this, you can see it has the, the level and the image. So here, when we have called this one, it will assign this level. So let's look at the level here. You can see the level is number 9, right? It's not 9. And this is the image. So you can see what I mean here is that this fashion data set, each data is given a number. For example, this is 1, 2, 0, something like that. And yep, so that's about the data. And we can look at the shape of the image, which is, we can see is 1, 28, 28, right? 1, 5, 28, 28, meaning that this is the shape of the image. Now, we already discussed that our data set, if we are using image, the shape of the data we want to train differs from what we have seen. So here we can see we have what we call the color channel height, and this is where height, this is a color channel. We use one here, remember, because the data, the image is gray, if grayscale, which we already discussed, that in complete sense, the shape of your image is somehow in this format, right? You have the badge size, the height, width, and the channel. This representation is what you call channel last, right? But we can also have channel first, which is basically allows you to have the channel at the beginning, not at the last. So you can see here, we have what you call batch. We have the height of image, we have the width of it, we have the channel, channel size. So this one can be either 1 or 3. If it is 1, the image is grayscale. If it is 3, then it means the image is, is not grayscale. And this is batch size. So we discussed what is batch size. Remember, batch size allows you to make one complete epoch, but the complete epoch is going through our data set through complete cycle. And the number of, we discussed this one also. I also discussed what is grayscale. So here, this is white, 1 up to 0 is black. So any number here is grayscale. So that's why we have 1 to specify our image is grayscale. For those that just join us, I'm just recapping what we discussed last so that we can build, so that some people, if they forgot. So here, so we can see this is our image size. So this is the grayscale, image height, image width. So we discussed that your image can be of this shape, CHW, that is channel first, or it can be actually this channel last. So you should know which kind of framework we are using. We said PyTorch, PyTorch generally accept this, can you see, as a default. So if we are working on PyTorch, PyTorch accept this at the default of what it's doing. So yeah. Okay, so let's look at our data. We have our train data, length of train data, train the data target. So we have 60 and we have 60 as well, which is the data is 60, the target is 60, because the training data and the level must be equal, right? So we have, so if we have in PyTorch, because if we have this is the train data that we downloaded, right? So if you want to see the data itself, which is the feature, we have the data. So this allows you to see the data. If you want to see, the target, we have the target. So this allows you to see the target. You can see each image is transformed, is given index like from 0 to 9, something like this, because we have 10 images. For the test data, we have 1,000 as well. And we can see this is the class names. So we can see 10 from uncle, this is the image. And we can see we want to convert this stuff to index. So we can see the shirt is 0, the trouser is 1. So this is the index of everything. Okay, so yeah, so that is that. We'll cover this, and here we visualize our data. So here we say show the image, this is the data. But if you want to visualize our image, because it's in this format, we have the channel, then the image height, the image width. We will not be able to visualize a data with this format because we have a channel. Remember, visualization doesn't require channel. So we need to remove this one so that we'll be able to visualize one of the data in the. So how can we remove one? We can call squeeze. Remember squeeze, what it does. So here we call squeeze. Now when I print, you can see like now the one shape removes is now there. So now image has 28 height and weight 28, then you can be able to, see it. So that's what we can do. So here you can see, we said PLT image show, image, the squeeze, can you see that? So when we call this, you can see it shows. So this is the essence we did that. And now here we go through everything here in the data set. And as well, we use the squeezing. If you look at them, squeezing, and we iterate and putting this on. So this is basically, downloading the training data. I believe now we understand how we can download the training data from use data set from PyTorch. Now, the next thing we discuss is preparing your data for training with data loader. So as we already explained that we don't train our model with the complete data. We divide our data into what we call data loaders. And we already also discussed why we need to train in batches because of several advantages such as memory efficiency, parallelization. If you have different batches of the data, you can parallelize them in different GPU, stochastic gradient descent, because if you are using different kind of batches, you can use what we call stochastic gradient, where for each batch you improve from the previous one. So before you go to the next epoch, you improve your training loop and accuracy. So this is good. So this is what we discussed why we need that. And that's why you see if the shape of your image must have the number of batches in some sense. So here 32, it means the number of batches we're going to train our model is 32. The image height is this, the width is this, and the channel is this. So that's the idea. So if we look at this one, the batches, so here we have our data set. You can see here it divided the data into batches. You can see from 0 to 32. From this is batch 1. The first one can give us 0, batch 1, batch 2, batch 3, and in each batch we have 32 samples instances. That is what we call batching. So we divide our data set into batch and up to the last one. Now, how can you create a batch from your data? So we use what we call data loader. We can see from torch.io import data loader. Now, data loader, you need to specify the size you want to do. So here we specify from 0 to 32, the size is 32. Now here we say, okay, give me the data in, you remember we have trained data that we already download. Now, data loader accept the data set. Which data set you want to put into batches? You say, the name of the data set I want to batch is called train data. It asks you how many batch sizes you want to divide the data. I say, hey, I want to divide it into 32 because I have to 32. It asks you, hey, do you want to shuffle the data? Because, maybe in the data set here, it's shoe, up to 1,000 is shoes, right? So you don't want that case. I say, hey, of course, shuffle my training data. So that's what these guys do. And now the next thing is test loader. There's something, this is the data set and this is the batch set, but don't shuffle the test set. So that's what we have here. You can see this. Now we can call, print this. So we can see train data loader. We have 1875, we have 1875, 1875 batches of 32. So remember our data is 60,000. So 32 times this number. So it will give you, for the test set, we have, I think 1,000. So 32 times this will give you, that. So that's what we discuss about that data loader. And then from there, we move into, how can we iterate through the data loader? So we discuss about what is called iterator in Python, which I already explained, but let me recap again. So here, let's assume we have a list, and now you can see this is a list. And now when I run this, I call this function iter on my list. What will happen now if I call this function called next on the return iter? So let's look at what will happen. It gives me 1. That is the first one. When I call this next on my iterator, it will not give me 1. It will give me what is the next item is 2. When I call iter, it will give me the next one. When I reach to the last one, it will give me an error like, hey, you finished everything. So the idea is, since we create a data loader here, we create data loader of this size. How many are they? 1875. How can we take the first one, second one, third one, next one, up to the when we are doing iteration? So the idea is we can use this, iter and next, so that we can be able to do. So this what we actually call here. You can see that. Then now the trend features and the trend levels are now assigned if after each one trend data loader. So so we can see here, we have the trend shape, that is the training data. You can see the batches now is in 32. The grayscale is 128 image height and width. You remember previously when we called this image 1 to 128.8 here, when we load the data set, if you remember. Yeah, you can see when we download the data, it's 128.8. That is, we have not batched the data, right? We didn't put into batches at that point in time, but now we batch the data because we want to train your machine deep learning. Okay, so why do we need to batch? if you are training deep learning, we use batches because it improves efficiency, it improves accuracy, and a lot of advantages. So that's why we did that. Okay, where are we? Okay, so here I call this, so you can see, and now we have the batch in 32, this, and the torch size is this. Okay, so putting all these things together, we download our data, don't forget, using dataset, partial MNIST dataset. We specify the data where it is. Yes, of course, train data, download, yes, transform the data into tensor, yes, because we cannot do anything except if it is tensor. And then test data, which is this, root data, test, yes, of course. Then we convert our data into data loader. So here, just recap, putting everything together. All right. So any other thing? Then now here we just, show the picture of one. So the first one, we download our data set, right? We download our data set. Here we can see here, here getting started with the data set, we download the data set and finish everything. Now we also prepare our data and put the data into data loader. Now the next thing is model training. Well, this one we also did it last week, but I think it's good we I'll go over it just to nail the understanding and build on top of that. So we see we want to build, we download the data, we now create different batches in the data. Now, what we want to do is when you want to train a machine learning models is basically you try to, create a baseline. When you create a baseline, which with simpler performance, then you build on top of it. So what we're going to do is basically now we're going to train a linear without what do we call this guy? Without non-linearity. Remember, we have the notion of linearity and the notion of what? Non-linearity, right? Okay, let me stop. Anyone with question before I move on? Anyone with question before I move on? Okay, I think we are all good. Okay, so we want to, because we said we want to build something baseline, which is very simple. So that's, we want to use linear. So we want to call this what we call platin, but remember our image is in this size, right? 32, 1, 28, 20, something like this. We want to do what is called platin, our image before we do anything. So let's look at it. So now here you can see we have NN model here. And now here I have my, let me run this guy. So when I call this X, my X here, I take the first, in the first batch, train future 0, that is the first batch, which is X here. Now I call platin here on top of the first batch. So you can see it is now the platin sufficient output, right? So now let me show us the outside. The X, the shape, which is the batch before platinum. Our output is the batch after platinum. So here we show them here. So you can see before platinum, the shape is, of the first image in this one is 128. Can you see that 28, right? But after platinum, it removed the one. We have, color channel and multiply this by this, right? So this is what you're gonna put into your model as sequential model, because sequential model need to have something very, sequential that you give it. So that's what we do. So we call the first model function MNIST version 0. Okay, we define a function here, input, hidden unit, output shape of our architecture we want to build, the input unit, the hidden unit. And now here we call super init, and we want to build a sequential model. So here we have the platin at the first thing, anything that is given into the data, the model, it will platin it and pass it to the linear layer. Here we can see the input features and the output features. They all receive the input and which is this input feature is input, output feature in the first layer. It should, hidden unit. We need to tell the model how many hidden unit do we want. That is hidden unit. And in the next layer, we already know that it must be, the feature hidden unit. The next one should not be input shape. input feature in the second layer. We remember the output of the first layer, which is hidden units, right? Number of hidden units, something like that. So here we already know this. I'm just going over there. Then we call the self here. So this is something that we have already seen before. Now here we see that this is linear, and now we have the model. We can build the model. We call it model 0. And now we can impute the model 0, what the model 0 takes. So we can see fashion MNIST, what it takes. It took the input shape, hidden unit, and output shape. So here we can see input shape. We want to give it 28 by 28. Hidden unit, how many hidden unit we want? 10. And output shape, the length of the class. So output shape, it must give you the, if you want to do classification, how many last item do you want to classify? Our image is 10. So that's why here we say length of class name, because class name give you 10 stuff. So yeah, you can see 1, 2, 3, 4, 5. So when we call length, it means it returns 10s here. So yeah, so when we call this is model 0, we can see this is our model fashion MNIST version 0. And now this model 0, we can, do training with it. But here they just try to create random data and input the random data to do some kind of model weight to show us. And now here we can see this. So this is basically, we create a model, but we have not trained the model yet, right? We just create the model called fashion MNIST. So what we want to do next is to see how can we create this, train this model, and now we can see the performance. Any question before we move on? Okay, so for us to train the model, we remember we need to define a lot of stuff: loss function, optimizer, evaluation metrics. And here, this is a helper function that provide accuracy function. Here, running this one, we'll download it. If we go here, I think the helper function, we can see it here. It is downloaded. And now accuracy function. This is the accuracy function. What it's doing is just this, then this. We call them how many Y true and Y predict. How many are equal? That is what is true and what is predicted. How many are equal? Then you sum them. For example, if they are 31, you sum them. And now convert them to item, meaning return a single number. Remember in PyTorch, that item will return a number, but here will return a tensor, the result, when you even sum them. So calling the item on top of them will return a number. And now here we can see accuracy equals to, so here it gives us the correct number, they are equal, right? Because where touch that ik means where is true is equal to prediction. You sum them, so you see correct. Now you can see accuracy is correct divided by number of prediction times 100. So this return accuracy, because this is how you calculate accuracy. So that's basically what we download here. And now we want to use it as accuracy here, but you can do many other things rather than using this one. We'll see more. So here we can see we define our loss function, which is cross entropy loss. Why are we using cross entropy? Can anybody answer us? Why are you using cross entropy loss here? Why are we using cross entropy? Can somebody help? But now, let me ask this one question. So if we have different kind of classification, right? If we are using binary classification, what kind of loss function are we going to use? If we are using multi-class class, what kind of loss function are we going to use in PyTorch? Can somebody attempt?
Yeah, just a binary cross entropy is for multi-class classification.
You say binary, we use what?
Cross entropy. Binary, we use binary cross entropy.
Okay. Okay. Yes, BE.
So also
yes.
use this for classification. We can use cross entropy loss for classification.
Yes, but what I'm saying, like for binary classification and for multi-class, binary a multi-class, for example, if I'm doing classification of 3 items, for example, to classify a tweet into positive, negative, neutral, you can see we have 3 classes. What about if I'm classifying tweet into only positive and negative, 2 classes? So you can see there are different kind of loss function we want to use.
We are using it for is this one is multi-class?
Yes, this is multi-class.
Multi-class problem.
So yeah, because our data set is multi-class, right? Because we have multiple classes, you can see them, 10 classes in fact. We have 10 classes, different image. So that's why we are using this one. All right. So, and now here, this is the optimizer. We're going to use SGG. The model, what is the model? Parameters. This is this because it's model 0. Our ladder rate is 0.1. So we run this guy. Now creating a function to timeout. So here is just creating a function to time how long the model take to train. So you can see print train time. It takes the start time. It takes the end time, and now here it defines the device. If it is in CPU, it will use CPUs. If it is GPU, it will use GPU. And here you can see here we total time inside the function is equals end minus start. So and it print total time that we, so it's basically calculating the time something happens. So here is an example. It can show you. So yeah, so that's that about that. Then we're creating a training loop and training model on batches. So now we have seen we define our, everything, setup loss, optimizer, evaluation metrics. Let's define the training loop. And before we go that, let's recap something here, which I already introduced. TQDM allows you wrap this guy, TQDM, inside this range. It shows you here, we can see we don't have, it didn't show us. That's what I want to show here. I also ask us to remember this stuff, what is enumerate doing. So here I have a list, eat, sleep, repeat. So when I call enumerate, it will basically here create an object. But when I create a list, I change it, the return of the enumerate, I call a list. This is what will happen. So it will tell me this is the first item, it, and it will give me the index, which is 0. Yes, of course. What is the second item? List, it will give me. So enumerate, return the index of the item in a list and the item. So we're going to use this idea, to show us, some stuff. So this is the training loss, training loop that we already discussed, where we stopped last week, week before last, I mean. And yes, so how does it happen? So let's go through it a bit. We can see here, I call the timer here. Can we see time to start training on CPU? I call timer because remember we create a function there. Okay, so I define the number of epoch. That is how many complete cycle I want to go through the data. Now for epoch in TQDM, that is for epoch. The first one, go, second one, third one, then the fourth one, it will not train anymore. That is what this is doing. For epoch in range of epochs, how many epoch, training loss. So here we declare the training loss of that we're gonna have. We set it to 0 because we have not even started training. Remember the goal when you train a model, when you are doing training, what is the goal? To find the training loss and test loss, right? That is the training loss. Remember, this is when you are training the model, you find out what the model learned on the training data. You also find out what the model learned on the test data. That is, you need to have train loss and test loss. So let's look at what happened. So here you can see we define train loss to be 0. Can we see that? Okay, now we want to train the model. Now, how can we train the model? In a train data loader, what it returns, it will return you the future and also the target, train data loader. But when we call enumerate on top of it, it will return the index, which will be assigned for batch 1. So here you can see for epoch in this. So we are now inside the epoch here. So, but inside the epoch, for one epoch, we have many batches. So we have 32 batches, maybe, for example, is inside one epoch. We have 32 or 50 batches inside one epoch. So we can see here, we enter into the epoch, one epoch, and now inside this, we have another loop, which will exhaust all the batches inside that epoch. So here we can see enumerate. We call on it, it will assign the indices to this. So if I have batches in my data set is 32 batches in each epoch. Though here we can see it will do one batch, it will take the next batch, it will take the third batch until it complete the 32 batches. Then if completed 2 batches, then it will go out from this loop and now go outside to the another epoch, training epoch, to take another look at the whole training data. So that is the idea here. Now here we said, okay, because here is training, we set the status is model train. We remember, then wipe we do a prediction. Can we model 0? We do a model forward pass here. We can see that. And now we calculate the loss. So this is a loss event. Given the true prediction by the true, it gives you a loss, right? And now here we calculate the trail loss. So here is the trail loss. So what is the trail loss? If you look at this here, that trail loss, we define it to be 0. So you can see it will say 0 plus loss. What is the loss? The loss you got here. That is the first batch. Now you go back to the second batch, you add with another loss. You go back to another, batch and do addition. So, and now here we have the optimizer. We grad 0 grad, which is the next step. And what is the first step is called backward function, right? And now here is to call the optimizer step. So these are the, key training step we already know. Then finally, you can see all these one, they are inside the batch. But after you finish everything, you want to calculate the trail loss. Trail loss, not on batches, but on that epoch. So here you can see we are inside one epoch. The first epoch, we can see that one here. And everything here is inside the batch. But now here we are outside the epoch for loop. We are inside now the epoch. So what is the total loss in that epoch? So the total loss we can see is equal to this guy trail loss. What is the trail loss? Can you see the trail loss that we accumulate for this batch? Can you see that trail loss? This divided by length of trail, something like that. So you can see this is what happened. So this is the trail loss for this epoch, right? Then what next is, testing. So remember we have trail loss and test loss. So here is the loss we have while doing the training. Remember when we are training a model, we talk about, the model is overfitting on training data, but it's not relying on test data. So here, this is something that we do now. We train on the training data. The trail loss will show you whether you are overfitting or underfitting or something like that on your data set. Yep. Okay, so what about the test? So test is still something. In the test, you can see here, we have, the test loss, we have also test accuracy. So here in also the training loop, you can also have test accuracy, but I think here they don't have that. We have only loss. So it is still something. We activate the context manager for evaluation. And now here we want to do inference, which is here context manager. We are not doing training. So if you are not doing training, we need to activate this. Then we call for X test and Y test. That is for the futures and the target in dataset loader. Do a forward pass using your model I train and calculate the loss, even prediction that is done on test prediction, and also, the Y test, and now calculate the accuracy. And remember here, because we are using multi-class, we sum everything using argmax. If you remember our previous sessions, we talk about why do we use argmax here. And test loss is here, and now test accuracy is here, and finally print. So when we run this guy, we can see here is training epoch 0, because you remember we have for epoch in this, so it will say, you can see for epoch 0 is doing training here. Any question? Okay, so you can see here what we print is train loss, test loss, and test accuracy, which we will have here, print here. You can see train loss, this is it. Test loss, which is this, and test accuracy, which is this. You can see here, this bar is what we have here, so that's that is it. Any question? Okay, so before the model, okay, we now have first and second epoch, then we have only one epoch remaining. So you can see here, it shows you 2/3. That is 2/3 epoch. You can see that 2/3. So that's what this TQDM is doing. It shows you like what you are doing, how long it remains, and whatsoever. Oh, okay, it's 3/3. We finished. So we can see here the, you can see the trend loss in the first epoch is 0.594. But if we see the trend loss on the, second epoch is 0.4763, on the third epoch is 0. It means our model is learning because we can see the trend loss, even the test loss is decreasing, right? So we can see this tells you your model is learning. If your training loss is decreasing and also the test loss are decreasing at the same time, then your model is learning. So anyway, our model is learning, and you can see here, even here, it has 82% accuracy. Here it has 83% accuracy. Here it has. But remember, what we are doing, we are using a model, sequential model without, non-linearity. So we can improve on top of that. Any question before we move on?
Yes.
Yes.
Yes, it happens sometimes. You can have your loss value reducing, but coincidentally or unfortunately, you will get your accuracy score reduced. I don't know what is happening.
You are not audible very good. Make it parakate.
What I'm saying, can you hear me?
Yes.
What I'm saying, you can have your training loss reducing, but accuracy reducing as well. For example, you can have your training loss maybe fall from 0.5 to 0.12, but your accuracy score can also fall from maybe 95 to 90 after you finish training.
Well, we can see it from here. It means your model, I think maybe there's something wrong, but from here, what we are saying is the accuracy here, we have 82, all right? The accuracy here is 83.19. The accuracy here is 83.42. So the accuracy here is increasing. Of course, you will have sometimes different kind of scenario where the accuracy may be misbehaving, in which case you are doing whether overfitting or underfitting or something like that. Of course, also if you have, for example, unbalanced data set, that is your data is not balanced, and only accuracy is not a good measure. So you need to use like macro average or some stuff like that if your data set is not balanced. So yeah, that's also another point. Okay, so we can see that the optimizer here, in each batch, remember here, in each batch, we are called optimizer. So it's updating the performance of model in each batch, So that's what we have. So you can see this is one of the advantage of mini batch over full batch. Instead of updating the model parameter after each epoch, we can update the model's parameter after each batch. This means our model will be improved for each batch rather than for each epoch, which is basically a good strategy for training model. Now, the next one is making prediction and get result. Now, we train the model, trace data. So sometimes you train your model, but you may have another separate data that you want to evaluate its performance, which the data set that is not used for train and testing, right? Now, that is what we call, evaluation mode in some ways. So how can you do that? So here we define a function called def eval mode. Model, what kind of model here? The function receive a model. That is the model you train, which the model you have, right? And you now have the data loader, the data is here, the loss function, the accuracy, because you want to return the loss function on the data you want to do the prediction and also the accuracy. And the data loader, you want to load the data, and the model, you want to specify the model. So we can see here, we, we set these guys, the loss and accuracy to be 0 because we don't have loss accuracy before we start. And now here we model a.eval, which enter into evaluation mode, right? And now here we can see context metadata because we are not doing training. So we call inference because we want to do prediction. When we say inference in machine learning, what we mean prediction. So we want to do prediction. Yeah. So unlike when you are doing training, we call what we call here model training, right? Where is it? Yeah, model train. Can we see model train? So yeah, inference. So here you can see for X and Y, TQDM, that is your data. Here we use TQDM. Okay, for X, Y in TQDM, data loader, because data loader return, tuple the futures and the targets. So make prediction here, forward pass, model X, which is the futures here. And now we want to see the loss. So the loss, you can see loss is equal to, the one we declare the loss is 0. So you can see 0 plus loss function is Y pred. That is your prediction with the target, which is the original target we can see is Y here, right? Which is we have the loss here. And also accuracy. The accuracy you have defined 0 plus accuracy function, which we already know it takes the true and prediction, using AGMA. So these are the, trend loss and accuracy loss. And now loss account and account to find average. So because here we are summing them, then we're gonna find the average. We divide them by the number of data loaders. If you have 32 batch, you divide by 32, something like that. By that. And here we call this. So when we create this function, can you see def? This is the function. Everything is here. Then it can input the model, the data loader, the loss function, the accuracy. We define them all here. Then it will return what it returns. So the model, the function returns. We can see the model name. We call model class name. This one in Python. When you call something that class, that name, it returns the class name, the name of the model or whatsoever. And here we can see the model loss. We say loss that item, because this loss, basically what it returns is tensor. So we call that item here. We can see then model accuracy, that accuracy here, because here we can see here is we have the true prediction, which is why, and now here calling this dim will change everything here to from tensor to this. So here we have accuracy here. And now here, when we want to just do the evaluation, we can call the model eval model. You can see eval model. What type of model do you want to evaluate? Model 0. The name of the model is 0 because we can see this. What we train here is model 0. We can see model 0. We train model 0 here. We can see that. And therefore, we can run this guy. So we can see it gives us an answer, right? So the model name, which I said is fashion empty because this is the model name we create. The model loss 0.47, model accuracy is 0.83. So you can see now we have the model loss, model accuracy, and stuff like that. So we do evaluation. Any question before we move on? Okay, so now we get our baseline. We need to improve through implementation. So as I said, when you are training machine learning model, the basic thing you need to have is just try to get baseline where you can build on. So now we have a baseline model, and now we need to improve. So you can see here, we are at this stage, right? You need to improve through implementation and whatsoever you need to improve. So let's look at how we can improve the model, because I'm working on CPU. I don't have CUDA here. We will still, if you are using Colab, you can still run it on Colab. Yep. Okay, so building better model with nonlinearity. So remember it there where we train the model does not contain any nonlinearity. And we learned in previous session that nonlinearity basically makes our model learn better. We can see here is all, we have flatten, we have linear layer, we have linear layer at the same time, right? So these are only linear layers we have. We don't have, nonlinearity. And so we need to introduce nonlinearity here, and the nonlinearity will help our model, we hope, to perform better. So that's what so this is the idea. So we can see after linear layer, then we add ReLU, which is nonlinear. After linear layer, we add ReLU. The same thing we saw previously, but rather here we just add nonlinear layer. So in a nutshell, what we are trying to say here is that, hey, there before we use nonlinearity, but here we we want to see improved performance, right? So let's add nonlinearity in that. So we add nonlinearity and let's look at what will happen. So we define the model here. We said now the model, we create another thing called model one using fashion MNC. And now you have your model called model one. We need to set up loss function optimizer and evaluation matrix. So we use cross entropy of using SGG as well, as we have shown here. And now, yeah. So the next thing, now we create a model and we define we define the model, instantiate the model here. We define the loss function optimizers. The next thing, naturally, remember, if you want to train the model, you want to do the, train step and test step, right? But what we want to introduce new is we want to functionize all this stuff. So look at what I mean here. This code looks too much, right? Look at it. 72 lines, right? And the thing is, if I want to train another model, because the steps are the same. Remember in PyTorch, I told you the training loss and test loss are the same. Now, if I want to train another model, 10 models, must I keep creating these things at the same time? But because they are the same, right? I need to copy this one to create. No, you don't need to do that. In programming, when we say, if you copy something twice, then it needs to be functionized. Yes, if at least you copy something twice, you use it in the same thing, you use it in another stage, then it needs to be functionized to make it function. So what we want to do is we want to functionize these ones so that we will only be calling them, just we don't need to repeat all these steps right in this. So that's the thing I want to show us here. Let's functionize them here. Why are they? Okay, let me copy them safe so that we can compare. Okay, I copy them. All right, so the first one we have is, here we have what we do in this code. We do training, right? This training, then we do tester, right? So let's create two different things. The first one is training step function, and let's create another function that will do testing. Now, for us to create a model function that will do training, what do we need to have for that model to have? So we need the model to contain the number of epoch, right? We need the model to, have input as train loader, data loader, right? We need the function to contain the loss function, right? That you're going to use, right? And what again? Okay, so let's go on there. So you can see train step. So we want to create a function called train step. So what does training step does? It will do this step that we are doing, but in a functional beta modularized way. You can see model, touch.model. Model. That is, this is called function annotation. It's just telling us what kind of return, what kind of type of this, which is model is, we are telling that this is a PyTorch model, touch.model. Yeah. Then data loader, we want to have the data that we want to train on, because we can see here, for us to do training, always we need to have train data loader whatsoever we need to do. So here we say, okay, you should have data loader, which is what type of it is data loader from PyTorch. Then we need to have loss function. Remember here, we need to specify the loss function we do to calculate it. So sometimes you can say, okay, the loss function is of different types. So you can specify your loss function. So we have a loss function, we have the optimizer, we have accuracy, then we have the bias where you want to do the calculation. And yes, so we create now the function, argument. Now the first thing we have is while doing the training is to set training loss. to 0. And here, because we want to also report training accuracy, we can set it loss to 0. So here we set train loss, train accuracy, they are all 0, 0. Because we want to report while doing training, we want to report what is the training loss, what is the training accuracy. Now, after we do that, what is next? What is next? Yes, we need to push our model, set it to training step. So here we can see, we set the model the train. So this is, training step. Now, what next again? We look through here, right? So this is it. For batch XY enumerate, you can see here, because this data loader will return X and Y, but the enumerate will return the index. So here we can see for batch, this. And now here we can see when we go here we make sure first we push the data into GPU whatsoever the device, because your model and the data must be on the same device. So we already defined device agnostic stuff, I think, previously. Here, we set the device. If you have GPU or CPU, here it will be set. If it is CUDA, it will select CUDA, which is GPU. If you don't have CUDA, it will be. So when you run this on Colab, it will have GPU in it. Okay, so after doing this, then we do a forward pass. Remember, we call model on our data. Then that is the first one we do in a training. What is the second thing we do in our training? We call a loss function, right? Loss function. Then here we have train loss. So train loss is accumulator, right? Which is the first thing we declare is 0. So you can see that. Then we have train accuracy for each batch. So train accuracy is equal to train accuracy, plus this guy as well. Train accuracy plus for you to. Yeah, so if you don't know, you already know, I believe, this is the same as this guy. So you can see this is train accuracy, which basically it has 0 at the beginning. Train accuracy is 0. Can you see that? But we say train accuracy 0 plus train accuracy, it will calculate the train accuracy at the first batch. So it will go back now, it will update the train accuracy is somewhere 20 whatsoever. So now it will go back to the next batch, do the next batch, obtain. And finally, we can see the optimizer, the loss backward, which we already have. And now the optimizer step to do that. So these are the 5 steps. Don't forget, these are the 5 steps needed in PyTorch to do training. These are the 5 steps. Do forward pass, calculate the loss, and if you want the accuracy, call 0 optimizer to 0 the gradient, then perform a loss backward to find the loss, and now call optimizer to find how to best to update those parameters so that you will have better performance. So now when we finish this one, then now here we can create, we create what is called train step, which basically do training. Then we want to also functionize the test step. So this is called test step. So it contains the same argument as you can see: model, data loader, less function, accuracy, and device, right? And now here we can see the same thing. It takes test loss and test accuracy. But here we are doing evaluation, because this is testing, which is evaluation. We can see we are using the previous one here. We are using not that here we are using model the train, right? Model the train. Here we are using model the evaluation because we are doing testing. So here also you define the step for testing. Here is we enter into inference mode for XY in data loader. Here you remember we are not training, so we don't need to have any two double loop. So here you can remember when we do the training, we have two. We have 4 batch in this one here. It goes here, and here also we have that, and we send this to device forward pass and calculate the loss. So remember, you can see here in the train, we have the optimizer step, we had the loss backward step, we had the optimizer step here, right? So all these steps in the training loss, we have them. Apart from train loss and accuracy. But in testing step, what we can see, we have put the model in the device, do prediction, right? When you do prediction, and now you do, calculate the test loss and test accuracy on this guy. So this is what it is. And now when we run this guy, we will have, our function. Now the next thing is, to do the training loop, right? Now, for us to do the training loop, remember, this is what we do. Basically, we define the number of epoch, then we calculate this guy for epoch in this epoch, then we enter into training, into training. Can we see that for training? This is the training. Then when we finish, we enter into the testing. So it means now here we need to, initialize this at the top before we do call our functions. So we need to initialize these guys. So here, this is what is happening. You can see I called touch the manual, I call the timer, and I call the number of epochs I want to do the training tree. Now for epoch in TGKM, print the epoch, which epoch is we are doing, we see what it's doing. But now train step. So you can see everything here we are doing in this step, all this one after printing here, all this one now they are now in a function. So I just call one function, which is this train step. Can you see that train step? You put the model, which kind of model you want to use. We say model 1. What is a data loader, train data loader, what is a loss function, what is the optimizer, what is the accuracy, which device, then you finish this one. Also the test set, you provide this one. And now when we run this, we'll start training. Any question? Any question? Okay, so it's training. And okay, so we can see now it's training first one, second one, and the last epoch. Because as described, we're going to use 3 epochs. So this is going into the last epoch here. And we can see, yeah, so we can see this is it. And now it takes these seconds. If you are in GPU, you will be able to see that maybe it takes less time than the CPU. And we can see the accuracy basically is 75, 61. It means even now, what do you think the accuracy does? The accuracy improve using non-linearity here, or it wasn't? Can you remember, what do we have the accuracy when we do non-linearity? What happened to the accuracy? Okay, let's go back. In the non-linearity when we did, what was the accuracy? We can see the accuracy, model accuracy is like around 83, right? The 83%, the model accuracy when we do with non-linearity previously. But we can see here now we are using linearity, non-linearity, which we're supposed to improve the performance of the system, but the performance decreases. So why is that? Any insight? Okay, so just take note, our model now we introduced non-linearity. Previously, we know that non-linearity actually improved the model performance, but here in this case, we see the performance does not increase. If we look at the result for our previous model, model 0, that this is for non-linearity without linear model, right? This is linear, this is it. It has 0.83. But here we can see the result for a model with linearity. Model accuracy is 79, which wasn't. Yeah, so what happened, we will be able to see it in the next session. So here we have seen we have not beat the baseline model. So you can see now, we say that what we need to do basically is to build a baseline model. When you build a baseline model, what you need to do is come up with different ideas, different ways to beat the baseline model, to make more stronger, have more stronger performance than baseline model. But in this case, we can see that we now introduce non-linearity, but the model performance does not increase, right? It even wasn't. So what can we do? So the next thing we're gonna do is we're gonna use different architecture that is even there for training image in deep learning, which is called CNN architecture. So CNN architecture is now, as I told you, we have different kind of architecture that can be used if you are using computer vision, if you are using text, NLP, for example. If you are using NLP, you can use RNN, LSTM. But when you are using images and vision, you use CNN stuff. But now in this today world, we have what we call transformers. So transformer we'll see transformer hopefully toward the end of our sessions. So transformers, they are basically, used and started for natural language processing tasks. If we can, let me show you Hugging. Okay, Hugging Face transformers. So if you are now doing the planning, now this is where the state of the art is. This website, if you look at this, is the AI community building the future. This is the based community where you can use already existing models. There is no community now, AI community more the world over this Hugging Face. In this Hugging Face, you can see there are many models from Meta, Microsoft, Google AI, or Grammarly, their model, and whatsoever. You can see it, home of machine learning. You can sign up here. You can do different things with this. You can do image classification, object detection, question answers with these Hugging Face transformers. They are called transformers, right? Yeah, so if we come here, you can be able to see models. So here, if you want to do different kind of tasks, image classification, translation, image segmentation, everything you can do with transformers. You can see that computer vision, this is kind of stuff you can even do with the computer vision. If you are working on natural language processing, these are some of the kind of tasks you can do with the Hugging Face transformer, translation, token classification, question answering zero. If you are using audio, multimodal, tabular, reinforcement learning, these are a lot of things you can do. We'll come over to transformers, Hugging Face, to see how we can, because at this point in time, in this current today, everything you do not everything, sometimes transformer may not be perfect, but what we're saying is that they are the one that now have the, that have the, that have had the data performance, Niger CNT. Okay, it's not here, right? Anyway, so let's move on. We'll come toward that. So what I'm trying to say is that we have, if you are using image or vision, CNN is the architecture, but now we have what we call transformer architecture. So we will also be able to see transformer architecture in the end. So what is CNN architecture? So CNN is a type of neural network that is designed to work with image data. So just to recap, I tell you that one of the main aim, if you are doing machine learning deep learning, is build baseline model. When you build a baseline model, you have a result. Try to improve it to improve it. Now we try to improve it, it doesn't improve. Now we want to move on and try to use the architecture that is designed solely for images, which is CNN. So you can see they are made of many other stuff, which is convolutional layer, fully connected layer, and whatsoever. And we'll be able to see that. I think now it's already 47. We have 10 more minutes for prayer. What we can do is we can stop, I think, here and go over to this one tomorrow and finish this chapter of, convolutional neural network, CNN in PyTorch. Yes, so I think we can stop here so that we can start fresh tomorrow on CNN. So tomorrow, since now we revise the previous session, tomorrow when we come over, we'll not do any revision. We can